Hello, good morning, everyone, and thank you for joining us today for our first Lowitja First Nations Health and Wellbeing webinar. Today we have a great presentation coming from Dr. Sungwon Chang of the University of Technology, Sydney, on statistics. Firstly, I'd like to begin by acknowledging the traditional custodians of the country throughout Australia and our connection to land, sea, and community. I myself am dialing in from Wadawurrung country, so I pay my respects to their elders past, present, and extend that respect to all Aboriginal and Torres Strait Islander people who may be joining us today. And so I would like to begin and introduce Dr. Sungwon Chang. I think, sorry, we might just be waiting. Sorry, everyone, just give us a moment to I'm not sure what has happened. There we go.
Hi, everyone. My apologies. Yeah. Can you
Some
all hear
technical
me?
difficulties, that's okay.
Okay. I will start my... Okay. Can you see my screen? My apologies, it's because I am so nervous in this.
Yep, we can see your screen, Sungwon.
Okay. So let's get started. Okay, thank you for your kind word, Kristy, and thank you for inviting me to join in this session. I'm providing a session on building a strong foundation, key concepts in statistics and epidemiology, and I'm hoping that this session will be helpful to you in your research endeavors. Okay. Before we start looking at data analysis or statistics, I would like to emphasize the importance of aligning your research purpose with some critical questions that you need to actually think about before you start on analysis section at all. So what that will do is that it will ensure that every step of your study is actually intentional and scientifically sound. And what that is the purpose acts as the foundation. So your research purpose acts as the foundation of your study, and it defines what the research is being conducted and what you aim to achieve. And this purpose guides all methodological decisions from design to data analysis. So what are these critical questions that you need to actually consider before you actually go on to the analysis? Well, the first question is, what is the type of the study design? Here we consider whether the study design is experimental, observational, cross-sectional, longitudinal, etc. And you need to think in terms that design needs to align with the research purposes. What I mean by that is that if you are thinking about looking at a study which talks about causality, so we're saying factor A causes factor B. If you're looking at something of that nature, we need to actually do a randomized control trial because that will be the best method to actually allow you to answer the question. So the design need to align with it. But if you are kind of looking at observing an outcome over time, then perhaps something like prospective cohort study is the right way to go. So even before the analysis starts, all of these questions need to be in your mind, and you need to actually consider, have I chosen the right design? Because you might have collected the data, which is fantastic, but it may not answer your research question or research purpose if your design is all wrong. Okay, moving on to the second question. What are the relevant populations? Identifying the target population is also very critical. So what do I mean by target population? The target population is the entire group of individuals that a researcher aims to study and draw conclusion about. It represents the broader group to which the results of a study are intended to apply. So are you studying adults with chronic conditions? So that will be all of the people who could possibly be in your study, but I am not. But you want to actually infer something about that group, or you want to actually make a statement about that group, or have some kind of description. And that is what is a target population is. And that is really closely linked with a third question, which asks, how will a sample be extracted from the population of interest? There are number of sampling methods, such as random sampling, stratified sampling, or convenience sampling, and they actually directly affects the representativeness of your study. At the end of the study, it's not just your group that you're interested in, but having some kind of understanding of what would happen in a bigger group. So if you have a poor sampling method, then this group that you have is not a good representation of target population. What that means is that generalization will be limited, and it will somehow actually introduce bias. And then we move on to what characteristics of the sample will serve as the target of the measurement process. This refers to the variables you plan to measure, like is it blood pressure, mental health score, or income levels. These measurements should directly relate to your hypothesis and research questions to ensure that the result that you get will be relevant and accurate. And then I guess the last question is, what is the statistical focus? Well, consider what statistical methods you would like to use to test your hypothesis. Are you looking at association between something? Or are you looking at predicting something? Are you looking at differences between two groups? So these things need to be actually thought out before you actually go in to do the study. And by thoroughly addressing all these questions, you ensure that your research is sound, focused, and is capable of producing the valid and reliable results that will add to the body of research. I hope that kind of makes sense. Okay. Now, let's establish that we have established the solid research questions and considered key study design elements. Now, let's kind of think about what do we mean by statistics? Well, statistics is more than just numbers and formulas. It's a powerful tool that helps us make sense of data and draw meaningful conclusions from it. It helps us to make sense of the complexity around us. It allows us to explore variability, the natural differences and fluctuation that we see in data. And sometimes it uncovers patterns that might otherwise go unnoticed. By analyzing data thoughtfully, we can move beyond individual observations to make informed generalization about bigger, larger population. And this process is fundamental in research, where we aim to draw conclusions that are not limited to specific sample. At the core of statistics is the definition is that it's a branch of mathematics that focuses on the collection, organization, analysis, interpretation, and presentation. I know that sometimes we kind of think, oh, statistics is just analysis. Not true. It actually starts from collection phase. And this might be the first step that you may take, where you gather the data for various means, and it could be surveys, experiments, or observational studies, or secondary data sources, but it's essential the data collection process is systematic, and aligns with your research objectives to ensure that it is accurate and reliable. And second step, which is also is a part of what we term as statistics, is organization. Once collected, data must be organized in a way that makes manageable and understandable. This often involves creating data sets, coding variables, and structuring the data into tables or databases for easy access and manipulation. And then we come to analysis, something that you kind of thought was what statistics was, right? This is where statistical methods come into play. And I guess that probably is the reason why you think of statistics as just analysis. Depending on your research question, you might use descriptive statistics to summarize the data, or inferential statistics to make predictions or test hypotheses. And you may have come across common techniques like maybe t-test, ANOVA, regression analysis, and sometimes like you might have come across like Pearson's correlations, etc. This is where it takes place in terms of the analysis. But statistics is not just limited to that. It also goes into interpretations because, as we all know, numbers alone don't tell the whole story. Interpretation involves understanding what the results actually mean in the context of your research question. Are the findings significant? And what does that mean? Do they support your hypothesis? Or are they potential biases or confounding factors that may not have been considered? And those things will enable you to actually utilize the statistics in the best way possible. And the final step is presentation. I just went too fast. Okay, final steps is presentation. And this is where you write up the papers, you kind of talk about the things so that at the end of the day, you will be able to communicate the results to a broader audience, so that it might be to the other researchers or policymakers or to the general public. By viewing statistics through this lens, it becomes clear that it's not just about crunching numbers. It's about making informed decisions and contributing valuable insight to the field of your study. Okay, at the core of statistics lies ability to make sense of data. And this is achieved through two fundamental branches which we talk about. One is what we term as descriptive statistics, another inferential statistics. Descriptive statistics are just as what it says. It describes the data. It describes any data process that is going to take place, and it describes who is in the study. They help summarize and organize the data in a meaningful way, allowing us to identify patterns, trends, and anomalies at a glance. So I kind of thought about where would you have seen descriptive statistics? In many research papers, the first table, often refers to as table 1, presents a summary of the sample's characteristics. This table typically includes demographic variables like age, gender, ethnicity, or some clinical variables like diagnosis or treatment groups, and other relevant descriptors. And this summarizes who is in the study, and it provides the readers with a clear understanding of who the study participants are and helps contextualize the results. And that's what I mean by descriptive statistics, and that's where it is utilized quite frequently. Another aspect about descriptive statistics is exploratory data analysis. It is a crucial but often underreported step in research process. While it may not always appear in published literature, exploratory data analysis helps researchers familiarize themselves with the data, and they identify outliers, those value which is far above what most people say. And it helps you to detect missing values and uncover initial relationships between variables. They utilize things like visual tools, which is like graphs, like histogram, scatter plots, or box plots, and they offer intuitive way to what the data distribution looks like. You know, you might have come across a term, something like bell-shaped curve or normal curve, or does it look very skewed? So it's kind of a really heavy on one side and it is not. It actually allows you to do that. So when you think about exploratory data analysis, that is a part of descriptive statistics. Think of it as like a detective work that guides further, more formal statistics analysis down the track. And that's what descriptive statistics does. Another important branch, or another very huge branch of statistics, is what we term as inferential statistics. Yes, we kind of recognize that descriptive statistics helps us to understand the sample, but inferential statistics allow us to make broader conclusions about the population from which the sample was drawn. Oops, I did it again, sorry. So you might have come across things like t-test, ANOVA, etc. That are some of the inferential statistics that would have been utilized. And the goal would be to actually make a conclusion and make predictions about a larger population based on the sample data. And they will include things like hypothesis testing, predictions, etc., or running a model, regression models, etc. Okay, let's look at descriptive statistic more in detail. Descriptive statistic can broadly divide into two main categories. Well, actually, there's three. One is a graph, but I kind of left that out because I think that you get the gist of it. In terms of measure of central tendency and measure of variability, I'm kind of assuming that you may have come across these terms in your field of research, but central tendency means things like mean, median, and mode. And what does it actually mean? It provides a single value that represents the center of the data, helping us understand where most data points tend to cluster. And when we talk about mean, I guess you probably know, it is the most common measure of central tendency, and it's calculated by summing all values in the data and dividing by the number of observations. Median, on the other hand, is a middle value when the data is sorted in an ascending order. And mode is the most frequent value in the data set. So there are what we term as three basic measures of central tendencies. And of the three measures of central tendency here, the mean is by far the most widely used because it takes every scores into account and is most efficient measure of central tendency for normal distributions, and is really good for people like us, statisticians, to develop statistical procedures for drawing inferences about means. But having said that, mean is not a good way to represent the middle value or the central tendency when the distribution is highly skewed or there are some outliers. But median, on the other hand, is appropriate when there is a highly skewed distribution. And what I mean by that is like most people sit at one end and there's only few sitting at the tail end. And yeah, so we can kind of have a think about that. And the mode can be informative, but should almost never be used as the only measure of central tendency, since it is highly susceptible to sampling fluctuations. Let's look at an example here. So if we look at data one, you will see that we have a score 2, 3, 3, 4, 5, and 6. And if I wanted to calculate the mean, it will be just adding up all of these scores, and there are 6 numbers, so I'll divide that by 6, and I'll get 3.83. If I was to find the median, it will be just ordering them, and the data set is ordered as it sits. And if I go to the middle, the two middle numbers are 3 and 4. And I find the average, and that will be 3.5. Mode in this case is the one that is occurring most frequently. And as you can see in the data, it will be 3 and 3. So it's 3 is the mode, right? And we can see that it kind of is, there's no outliers. What I mean by that is there's no one value that is sitting outside what most people are saying. And then you can see that mean, median, and mode is kind of similar. They're not identical, but they're kind of sitting around about 3 mark. But if you look at data set 2, you see that 2, 3, 3, 4, 5, and then I changed 6 to 600 to kind of show you what would happen when we have an outlier. So 600 is an outlier, or it could be an error, right? But it is, let's kind of say it's an outlier. So somebody kind of have 600 in that data set. If I found the mean, when I add up all the scores and divide by 6, I get a mean of 102.3. But do you see when I find median and I kind of go, this is ordered, so I go to the middle value, and in this case, there's 2, which is 3 and 4. And when I find the average, it is still 3.5. And the mode is 3. And that is the probably reason, that is the main reason why people say, hey, when you have an outlier or when you have these extreme values, when the distribution is not bell-shaped and really nice distribution, then sometimes median might actually represent the data much better than the mean. I don't know whether you kind of have noticed it, but when you're reading an article and then instead of mean, when they talk about averages, they might have put something like median. The reason they do that is either because there is a small number of data and they're trying to see whether median might be a better representation, or the distribution is really skewed. So that is a kind of a clue. And I guess variability is another measure that we utilize in descriptive statistics. It describes how spread out the data is, indicating how much variation or dispersion exists in the data set. First is something that you kind of know really well, the range, right? Range is something that you've seen and understand. It just means the largest value, take away the smallest value, and it gives you a spread of the data, right? But if you kind of think about it, they kind of think, hang on, mean was pretty good because we utilize all of the data in the study by utilizing the actual values. So can we do something like that with the spread as well? So they kind of came up with this thing called variance. What that means is that they look at each of the data points and look at how far it is from the mean, and then they try to average that out. And they said that probably is a pretty good measure of dispersion. Only problem is, you know how statisticians or mathematicians, they can be really a bit nerdy. It is very important for them to actually talk about minuses and pluses, something that is negative and something that is positive. They notice that when they just average it out, it comes to 0. And to avoid that, what they did was they actually squared the distance between each of the points to the averages and then find the average of that. What that actually did mean is that when we're talking about units, the units are also becoming squared. So it's not just the value that gets squared, but actually the unit of the measures gets squared. So if we're talking about height, right, and we measure the heights in meters, then variances is expressed as meters squared, which means it's kind of very hard for us to actually understand what that actually means. So what did they do? They square root the variance, and we call that the standard deviation. I hope that makes sense, right? And that usually in the publications, standard deviation usually accompanies the mean. So when you have the mean, they usually talk about standard deviation. So it has it right next to it. What is the interquartile range? I was kind of deciding whether I should include that. What that actually talks about is in any of the distributions, it kind of just went without me saying it, so my apologies. What it actually means is that you divide the distribution into 4 equal parts, and the third largest point whether it's 4 divisions, take away the Q1. So that's what it means. Only reason I present that is in the literature, you will see that interquartile range usually accompanies median. So it is true sometimes median and they report range, or sometimes they do median and interquartile range. So I hope that you kind of get some understanding of how the measures of central tendency and what is the measure of variability. And I guess it is very important to kind of understand that it gives you a summary of what is there. So if you have a large number of people, how do you describe that with just 1 or 2 numbers? And the way they chose it was measure of central tendency and measure of variability. Okay, since we kind of have talked about descriptive statistics, let's kind of think about what we mean by inferential statistics. Inferential statistics are at the heart of research because they allow us to move beyond the data that is in front of us and make a broader conclusions that can inform healthcare. I don't know why this is doing this. My apologies. It just seemed to be going to the next slide. Okay. So that it helps us to beyond the data we have in front of us and make broader conclusions that can inform healthcare decisions, policy changes, and further research. But with that power comes responsibility. Understanding the uncertainty and limitations involved in is key to drawing accurate conclusion. So what is inferential statistics? It is a technique that allows us to take data from sample and make predictions or generalization about a larger population. This is different from descriptive statistics, which simply summarize the data we have without trying to make broader conclusions. For example, if we had a survey, we carried a survey, and there were 200 people about their exercise habits. Inferential statistics helps us to make educated guess about the exercise habits of the entire population, not just those 200 individuals who are in our study. The key idea is that we are using a small piece of data to understand something bigger. But because we are working with a sample, there's always some uncertainties involved. The common techniques of inferential statistics are hypothesis testing, and this is a formal method to determine whether the pattern we see in the data are likely due to random chance or if they reflect true effect. For example, is a new drug really more effective? Or are the results we are seeing just a fluke? And it actually helps us to determine that. Confidence interval is another area that, or another technique that is used in inferential statistics. And confidence interval gives us a range of values where we believe the true population parameter lies. For example, we estimate that the average weight of a population is between 68 and 72 kilos with 95 confidence. It means that we are fairly sure the true value lies within that range. And then there is what we term as regression analysis. Regression is used to explore relationship between variables. For instance, we might look at how age or diet influences blood pressure. This helps us understand which factors are linked and how strong those relationships are. And that is one of the techniques that we use. So, what is the goal of inferential statistics? As I mentioned in previous slides, goal is to use data from our sample to make informed decisions or predictions about a larger populations. However, since we are working with sample, we always tend to be cautious about random variation. Sometimes patterns may emerge, especially in small samples, and we kind of wonder whether it is just a fluke or whether it is not. And this helps us to actually decide whether what we are seeing is likely to be real or just random noise, really statistical term, for a fluke, right? Okay, let's look at choosing the right statistics. Choosing the right statistics is crucial for ensuring the validity of your analysis results. The goal is to match the test to the data you have, and then to the question you are trying to answer. So let's walk through the steps for selecting the right test. There are 5 key considerations. The first step is, once again, understanding the aim of your study. What is the specific research question you are trying to answer? Are you comparing groups? For example, do you want to see if there is difference between 2 or more groups in terms of a specific outcome, such as comparing blood pressure levels between 2 different groups or 2 different treatments or groups? Or are you looking at a relationship between variables? Example, do you want to explore how age is related to income? Or are you testing a hypothesis? For instance, you might want to test if a new drug has a statistically significant effect on reducing symptoms. And understanding that will help you to guide what test to use. And the second step is data type. It is important to identify what is the outcome data that you're working with. And if you kind of, if you kind of think about it, I guess the broad way that you usually think about is categorical or continuous, and that's what you'll see in the slides. But even within that, there is different types of data. There is what we term as nominal data, and this is categorical data with no order, such as gender or ethnicity. It's just a number that has been attached to describe something. So it is a categories. And then we go one level higher, which is ordinal data. This is category data with ordered ranks. And if you think about education level, there's like a primary school, high school, university, etc. So it could be something of that nature. But ordinal data that you definitely have come across is Likert scale, strongly agree, neutral, disagree, strongly disagree. Well, there is no, it's a descriptor. So it's a categorical data, but it is also ordered. So depending upon how you attach the score, so 1 might be strongly agree, 2 might be agree, 3 might be neutral, 4 might be disagree, 5 might be strongly disagree. There's an order to the system, but it is categorical. What that means is that, I don't know whether you thought about this, but what that actually means is that if I kind of got somebody who is a strongly agree compared against agree, the distance between them may not be same as somebody who's, say, neutral to disagree. So, and that would be one of the reasons why we kind of classify them as categorical, and types of data analysis or the test will be very different. And then we have continuous variable. There's a difference, there's a interval and ratio data, and there's a slight difference between them. Interval data are things like temperature, or it could be things like, blood pressure. What it actually means is that it doesn't have a true zero. What that means is when there's 0, it does not necessarily mean that there's no absence of it. So that's interval data, and ratio data actually allows you to see that. So it is things like age, height, weight, all of those things are termed as ratio data. And sometimes it is kind of looked at as a quantitative data. And if you have those sort of data, the kind of analysis you choose will be very different. But these are the questions that you need to actually think about before you choose the right test for the data that is in front of you. And the third question is how many groups of variables you're working with. So say that you're looking at blood pressure, how many groups are in your study to actually make the comparison, for example? You might have 2 groups. Are you comparing between treated and control? If so, you might consider a t-test for comparing means. Or you might have more than 2 groups. Then you might kind of use ANOVA. So it will kind of direct you to a different types of analysis. And if you're exploring relationship between more than one variable, you might use correlation test for continuous variables, or a chi-square for categorical variables. So it kind of leads you to a different types of tests. And then there's what we term as checking the assumptions. Statistical tests often come with assumptions about the data. These assumptions must be checked before applying a test. And usually, the one that is most common is normality. Many tests, such as t-tests or ANOVA, assume that the data follows a normal distribution. So if your data is not normally distributed, then you have to use another test. And usually we call it non-parametric test because it doesn't kind of say it comes from certain distribution. But having said that, that's great, but it's not as powerful as parametric tests, things like t-tests, ANOVA, etc. Another assumption that usually you need to actually check is homogeneity of variance. This assumption refers to the idea that the variability within each group is roughly equal. If variances are unequal, then you can use the tests like t-test, ANOVA, etc. You just need to use adjusted tests like maybe Welch's ANOVA test. Okay. Another thing that you need to actually also look at really carefully, and it's not necessarily assumption, but it's a sample size. Some tests are more robust with larger sample sizes. If you have small sample size, you may need to choose a non-parametric test or adjust your approach accordingly. And then you're ready to select the appropriate test. Rather than giving you a whole list of the tests, I just thought that it would be good to actually give you what are some of the things that you need to actually consider before you do choose the test. Because I think there's a lot of articles, a lot of chapters which is kind of talked about, which test to use. So having a look at that, I think you will kind of see what I kind of mean. Yeah. So choosing the right statistical test requires careful consideration of the research question, data type, number of groups, and underlying assumptions. By systematically following these steps, you can ensure that your analysis is both appropriate and reliable. I encourage you to always double-check the assumptions of the test you select. And if necessary, consult resources or software or talk to your friendly statisticians. Okay, just to demonstrate the point, what you actually see is a measure of level of measurement that I talked about, data types. So if we have a nominal, ordinal, interval ratio, and since we kind of looked at measures of central tendency, you know, mode, median, and mean, or you kind of have some understanding. If you look at what we chose, you will see that if it is nominal, the most important measures of central tendency would be the mode. Yeah, you can't do the mean because it kind of doesn't make sense. Yeah, and the measure of variability might be range or frequency distribution, or what is the percentage of who lies in there. And then, or if you have an ordinal data, which kind of talks about is a categorical, but it shows a ranking, then sometimes mode or median is also appropriate. And along with that, you'll have range, percentile, etc. But if you have interval or ratio data, then you can use all of those: mode, median, and mean. Yeah. So I think this example kind of shows you what I mean by data type actually decides what kind of methods that you'll use. Okay, so let's start with what we mean by hypothesis testing. Hypothesis testing is a method we use to figure out if what we are seeing in our data is real or just a fluke. Imagine you're testing a new medication. If patients improve, how do you know it's because of the medication and not just random chance? Hypothesis testing helps us to answer that question. It's basically a decision-making tool that helps researchers determine whether the patterns in the data are meaningful or if they might have happened just by accident. And in hypothesis testing, we talk about two hypotheses. The first one is what we term as null hypothesis, and null hypothesis is actually the one that we test, but what it usually says is there's nothing going on. It assumes that there's no difference, no effect. For example, the new drug is no better than the old one, and that's what it says. So it usually goes against the research hypothesis or research question. Because if you think about why you're doing research, you're doing it because you think that there's something going on, right? But null hypothesis says nothing is going on. The alternate hypothesis is the opposite. It suggests that something is happening, that the new drug does work better, or that there is a connection between smoking and lung diseases, etc. So think of the null hypothesis as the default position, and we assume it's true unless we have strong evidence to say otherwise, okay? So, and all the hypothesis testing is carried out in the assumption that null is true, that nothing is happening. And we're trying to find whether we can find sufficient reason to say, no, that's not true. So we collect the data, right, from our study or experiment, and then we analyze it to see if the results are strong enough to support the alternative hypothesis. And if the data shows strong evidence against the null hypothesis, then we reject the null hypothesis. But if there isn't, then we say that if there isn't strong evidence, then we say the null is true. So it is very conservative in how they carry out the hypothesis testing, because we start with a baseline, which kind of says nothing's going on. So prove me or show me that there is actually something going on for us to be excited about. And I guess at this point, you might kind of say, is it kind of linked with p-value in research? And you're absolutely right. The p-value is kind of one of the most commonly used statistical concepts, but it's often misunderstood. In simple terms, the p-values tells us the probability of obtaining the result as extreme as the one that we observed, assuming that nothing is happening or the null hypothesis is true. Null hypothesis generally state there's no effect or no difference between groups, etc. Remember, that was the heart. So when we find a p-value, which is small, it suggests that observed data would be unlikely if nothing was happening, leading us to consider rejecting the null hypothesis. However, if the p-value is really, really large, then it suggests that data is consistent with the null hypothesis, which means that there's nothing going on. And when we are interpreting the p-value, I know that we get really excited about 0.05 or p-value of 5%. What it actually is a conventional cutoff point for statistical significance. But, there are some people who kind of argue, what's the difference? Is there a huge difference between 0.06 and 0.03? And it is one of those things that you just need to consider in terms that if p-value is higher than 0.05, doesn't necessarily mean that there's no effect. And if it is under that, so it's like 0.03, does that mean that something's going on? And I guess that's something that you just need to actually think about, right? And I'm kind of assuming that's where you would have seen the p-value. In terms of misinterpretation of p-values, one of the biggest misconceptions is thinking that p-value actually represents the probability that the null hypothesis is true. This is not true. This is not correct, right? The p-value tells us about the data, not about the truth of the hypothesis. Similarly, people often think that a smaller p-value indicates a larger or more important effect. This is also not true. The p-value only speaks to the likelihood of the data under the null hypothesis. It doesn't measure how big or meaningful the effect is. For that, we need to look at effect size or maybe confidence interval. So it's critical to understand that statistical significance does not equal practical significance. Any small effect in large data set actually can produce a very small p-value, but that doesn't mean the effect has real world importance. And there is some limitations which is kind of linked with this. As I said, the p-value is heavily influenced by the size of the sample. With a large sample size, even a trivial difference can become statistically significant. And in a small sample, something that is really large effect may not have the sufficient power to be significant. So that's something that you need to watch out for, as well as the multiple testing problem. If you carry out lots of tests, then there is a chance that something might seem to be significant when it actually isn't. So I don't know whether you heard of the term Bonferroni's correction. That is kind of utilized when there's a multiple comparisons happening in one data set. So p-value doesn't provide a complete picture. It should actually be interpreted alongside confidence interval and effect size to understand. I'm going over time, so my apologies. I'll try to get through as quickly as possible. Okay, hypothesis testing and confidence interval, they are both very important, but they look at different things. Hypothesis testing actually determines if there is an evidence to support an effect. So it kind of says, is there an effect? Yes or no? And that's why, they kind of talk about statistical significance as if it is a big, important terms, right? Whereas confidence interval actually looks at how large is that effect? What is the true value? What is the place where it will sit, right? And within that, there's also something that you need to actually think about when you think about confidence interval. You've got to consider how large is that range, right? From the low confidence level to a high confidence level, right? If it is really narrow, then it's very precise. So it is very good. But if it is really large, then it's not that good, right? And I kind of talk about to my students at least anyway, think about what marks that you can get. You can be really confident, but mark that I'll get from 0 to 100, it doesn't tell me anything. But if I say I'm 95% sure, the mark that I will get is between 50 and say 60, it gives you a lot more understanding of what's going on, right? So that's something that you need to actually consider. We recommend that you use both of them, right? Because one is talking about, is there an effect? Another one is talking about how large is that effect? So it will be a good idea for you to actually go through and utilize both. Okay, I'm really going to rush through this. One of the things that you need to consider when you're doing a data analysis is whether there is a missing data, right? Because missing data can actually bias the results and distort the results, and it might reduce the validity of the conclusion. So you might have a group of people in your study who represents the true population, but while you are in the process of the research, there are some people who did not respond, or there might be some people who kind of dropped out. Then the group that is left over may not look like the true population. And I guess that's our target population. So that would be one of the reasons why missing data is really important. So look out for it. There is a kind of a way to get around it, like imputation, or you kind of replace some values or something like that, or you kind of stop that from happening. So make sure that there is some procedure in your research activities that kind of stops the missing value. And I guess effect size is also something that is really important because it measures the strength or magnitude of relationship or differences between variables in the populations. So go more than just statistical significance, and think about in the practical and real world importance of the findings. And degree of relationship is something that is also something that you need to think about. This is a kind of making sense of statistical relationship in the data. We often want to know not only if there is an effect, but also show how strong that effect is and whether it is or whether it matters in practice. So that's something that, and I think multiplicity, I kind of talked about it in my previous slide, and clinical significance. Statistical significance is fantastic, but if it does not mean anything in the real world, then you've got to ask yourself, is that really important? So ask, about those things and think about those things and see, if clinical significance matches the statistical significance, because sometimes we do statistics and that's a tool, right? But at the end of the day, it is a clinical significance that you kind of want to talk about. Okay, let's talk about interpretation. When interpreting the results, it's crucial to link them back to the original research question. We need to be careful not to overgeneralize or misrepresent what the data is actually telling us. For instance, a statistical significance result might not necessarily be practically meaningful. It's essential to balance the statistical outcome with real-world context to ensure the findings are both accurate and relevant. And we got to have credibility, right? It's all about trust. So build a trust and be very transparent in your methods and data reporting. Clearly outline how the data was collected and analyzed helps others to understand and trust the process. Generalizability, I think I talked about it in the other slides, so I'm going to go to robustness because of time. Robustness speaks to the strength and reliability of our findings. Is ensuring that results remain consistent even when we change certain assumptions or models. Okay, so so one way that they get around it is they kind of carry out what is called a sensitivity analysis, which they carry out to ensure that the result they get is quite robust. Final slide that I want to talk about is statistical conclusion validity. It refers to how accurate and reliable our conclusions are when assessing relationship between variables. So have you I don't know whether you might have seen low statistical power. What it actually means is there is an effect, but it's not able to capture that if it is a low statistical power. And it is kind of linked to the sample size. The larger the sample size, the more power it has. And that's why people like large numbers when they're doing a statistical test. And violation of assumptions, I talked about that in the previous slides, as well as repeated tests also has been talked about. And another thing is unreliable measures. If your tools or methods for collecting data is not consistent or accurate, the conclusion we'll draw will be questionable as well. So to improve statistical conclusion validity, increase your sample size to ensure that you have enough power, use the appropriate statistical test, and ensure that you meet all assumptions, and maintain transparency and avoid data manipulation. Don't do cherry picking, right? And the key takeaway here is the rigorous study design and careful analysis are critical for drawing valid, trustworthy conclusion. Thank you.
Amazing. Thank you so much, Sungwon. We just unreal being able to run us through all of those things, and I think it's been very helpful. We've already got some questions in the question box. So for anyone else who would like to ask any questions for the next, we've got 4 minutes left. Please put them in the question and answer Q&A function in the bottom of the screen. But to start off, we've got one already, and someone asked that if they have an odd numbered data set, is the median just the middle value?
Yes. So you order the data and you kind of take away. This is what I do. If I was to do by hand, I'll order them, take away the smallest, largest, and go all the way to the middle. If it's just one number, that will be the median. But if there's a two, like one we had that in our example, it's the average of the two. So yes, you're spot on. It will be the middle number.
Thank you. A second question that we have is, what are the most important things to consider to determine the minimum data set needed for there to be a meaningful analysis?
I guess I'm not quite sure which aspect you're talking about. What is the minimum aspects about the data? Do you mean just need to get clarification? Are you talking about the number in your study, or are you talking about some other things? If it is a number in the study, in order to have a the study that is quite able to pick up the differences, so it has sufficient power. Usually we talk about calculating the sample size. I'm assuming that that's what the question is. referring to. But if not, you should get, so the whole idea of the sample size calculation is don't have too large so that even the small blip will come out to be significant, but don't have too small that is not powerful enough to pick up the differences. So my suggestion would be to calculate the sample size before you start your research project. Then it will give you a clear indication of what is the appropriate number. So when you say minimum, that's what I'm kind of thinking, sample size. But if it's not, my apologies. But another thing that kind of talk about is, if I want to do a t-test, what is the, rule of thumb number that I need to have in my study? Usually we kind of say 30, right? But I've seen studies where they didn't have that, but they kind of still did it anyway, right? But we kind of say in order for you to have a kind of a decent analysis, you probably need around about 30.
Thank you, Sungwon. I think that is all we have for questions, which is probably perfect timing with it being 2 minutes left. This webinar will be available on the Lowitja YouTube channel. A link will be posted in the chat, and also a link to the Lowitja First Nations Health and Wellbeing Journal will be posted in the chat as well. Again, Sungwon, thank you so much for taking the time today for this webinar and presentation. We appreciate it, and we are very appreciative of you taking time out of your day to educate and give some help our early career researchers with statistics.
Thank you. Thank you for the kind invitation. I hope that I didn't bamboozle everybody and they kind of
It was
turned
amazing.
over stats.
No, it
Oh,
was
I didn't.
amazing. It was perfect. Thank you so much, Sungwon. And
Thank
thank you
you.
everyone for your attendance today. We will be doing webinars approximately every 2 months on various different topics. So please keep an eye out in the Lowitja Doris and other avenues for our upcoming webinars. Everyone have a lovely day.